Year 13, probability revision. So we start with a conditional probability question about a cat who's going to decide whether to spend the night inside or outside the house. So this is really setting us up for a tree diagram. Let's have a look at what we can do here. So we know that Arthur the cat spends Saturday night inside. So we know that if we have a starting point on our tree diagram, Saturday was spent inside. So the next layer of branches can refer to Sunday. And then after that, the next layer to Monday. So the cat can either be inside or outside. So let's set up our branches. And we know that if the cat spends a night inside, the probability he will spend the next night outside is 0.6. So because he spent Saturday inside, the probability that he will spend Sunday outside is 0.6. So we need to make sure we've got 0.6 here and 0.4 here. And then if we follow the branches for Sunday being inside, the probabilities will repeat, 0.4 and 0.6. Now, if Arthur spends a night outside, then the probability that he will spend the next night inside is 0.9. So Saturday was spent inside. Let's follow the branch for Sunday being outside. So this probability here is going to be 0.9 and this one is going to be 0.1. We now have to calculate the probability that Arthur will decide to spend the next Monday night outside. So let's look at all the branches that allow us to get to Monday night being spent outside. Got inside, outside, outside, outside. So the probability will be 0.4 multiplied by 0.6 plus 0.6 multiplied by 0.1, and that comes to a total of 0.3. Now, part 2, show that it is extremely likely that Arthur will spend at least one out of the next 7 nights, Sunday to Saturday, inside. So, working out the probability of at least one night being spent inside would involve a lot of different paths, because you'd have to look at the possibility of there being 1 night, 2 nights, 3 nights, 4 nights, 5 nights, etc. And then you'd have to look at the different combinations of those as well. So the probability that he spends at least one night inside can be worked out much more easily by doing 1 minus the probability that no nights are spent inside, because that's the only option we're not covering. At least one means one or more, so the complement to that, or the opposite to that, is 1 take away the probability that he spends no nights inside. So that is going to be the following. So we want to look at the following paths. Saturday was spent inside, but Sunday must be outside, which is 0.6, but then outside probabilities after that are all 0.1. So it will be 0.6 multiplied by 0.1 to the power of 6 for the 7 nights. So that is Sunday, and then these ones are Monday through to the next Saturday. We of course have to do 1 take away this value, and this gives us an answer of 0.999994, which is really very, very close to 1, which means it's extremely likely. Now, the key to this question was understanding that if you're working out the probability of at least one thing occurring, it's often a lot easier to do it as a calculation of 1 minus the probability of it never occurring, because then you only have to take one probability calculation and subtract it from 1. Let's look at the next example. So a particular condition affects 0.8% of the population. 90.1% of the population as a whole carry a certain gene. 9.85% of the population carry neither the gene nor are affected by the condition. Paul discovers that he carries the gene. He believes it is very likely that he will be affected by the condition. Determine whether or not he is correct. There is so much information going on here. So we have two situations. We have a condition that affects some of the population, and some of the population carry a particular gene. So I'm going to say that C is the event that the condition affects someone in the population. And G is going to be the event someone carries the gene. So we know that the probability of C is 0.8%, which is a probability of 0.008. And the probability that somebody has the gene is 90.1% or 0.901, converting these percentages to probabilities, decimal probabilities. Now, 9.85% of the population neither carry the gene nor are affected by the condition. So we can say that's the probability that someone is not affected by the condition and they do not have the gene, and that is 0.0985. Now I can represent this information, if I like, on a Venn diagram. There's obviously an intersection between people who are affected by the condition and people who have the gene. And the key piece of information to fit in our Venn diagram is this piece of information here, that people who do not have the condition or the gene, that's 0.0985 here. Now that means the union, which is everything covered within the total of these circles here, is 1 minus 0.985. So the probability of C union G, that's condition or gene or both, is 1 minus 0.0985, which comes to a value of 0.9015. We can then make use of the addition rule, which tells us that the probability of C intersection G, which is this portion of the Venn diagram, is equal to the probability of C plus the probability of G, take away the probability of C union G. So that would then be equal to 0.008 plus 0.901 subtract 0.9015. And that comes to a value of 0.0075. So quite a small probability there. And we can then fill in the other portions of the Venn diagram as well if we wish. So this portion must be 0.0005 and the other portion must be 0.8935. So we've subtracted the 0.0075 from these two values here. Now, let's go back to the question and see what we're being asked to find out. Paul discovers that he carries the gene. He believes it is very likely that he will be affected by the condition. So this is a conditional probability because we know in advance that he has the gene. We are trying to work out the probability that he is affected by the condition given that he has the gene. So we need to make use of the law of conditional probability, which is that C given G equals the probability of C intersection G divided by the probability of G. Now, the probability of the intersection is 0.0075, and the probability of G is over here, it's 0.901. So this is the probability that Paul is affected by the condition, knowing in advance that he has the gene. It's conditioned on him having the gene, or us knowing that he has the gene. Now this is 0.008324 ... So I'm going to round that to 0.0083 to two significant figures. This is a really small probability. So actually, he's not correct. It's very, very unlikely. So a small probability, so very unlikely for Paul to be affected. He is wrong, or he is incorrect. We must answer the question there and address that. So moving on to example number 3. In a game show, each contestant is asked a number of questions. Each question has a choice of 3 possible answers. The probability that John knows the answer to any given question is 2/5. If John doesn't know the answer, he guesses. The probability that he guesses correctly is 1/3. Calculate the probability that John answers 2 consecutive random questions correctly. So I'm going to display this information on a tree diagram. So if we look at the first possible scenario, he knows the answer with a probability of 2/5, which means he doesn't know with a probability of 3/5. Now, he could be correct at this point, or he might be wrong at this point. So if he doesn't know the answer, he's either correct with a guess that's going to be correct with a probability of 1/3, or he's not correct, C dash, and that of course will be a probability of 2/3. So this is one question. This part of my tree diagram represents one question. So the probability that he answers question 1 correctly, well, we need to look at all the possible branches of the tree diagram that take us to this correct answer. So I'm going to try and highlight these. So he could either know the answer, which is a probability of 2/5, or he may not know the answer, but he may then guess the answer correctly. So how do I work out this probability? It's 2/5 plus 3/5 multiplied by 1/3. So that gives me an answer of 3/5. Now, we then have to essentially look at him repeating that for 2 questions. So the probability that he answers both correctly, assuming independence, will simply be 3/5 multiplied by 3/5, because the tree diagram would just repeat itself. So the answer is 9/25. So on to the next question. The probability that Judith has meat for her evening meal is 0.2. And the probability she has fish is 0.35, otherwise she has a vegetarian dish. And then we've got some conditional probabilities that come up after that. Make sure you've read them really carefully. Now, we are told that last night Judith had indigestion. Calculate the probability that she had meat for her evening meal. So it's a conditional probability question. We're told she's had indigestion, so based on that fact, that condition, what is the probability that she actually had meat? So this is really asking us to set up a tree diagram so we can see exactly what is happening. So the 3 possibilities for her meal: she might have meat with a probability of 0.2, she might have fish with a probability of 0.35, and the other option is a vegetarian option, which would have a probability of 0.45. Now, if she has meat, the probability that she has indigestion is 0.8, so the probability she doesn't have indigestion after meat is 0.2. If she has fish, the probability that she has indigestion is 0.5, the probability she doesn't have indigestion must then be 0.5, and if she has a vegetarian meal, the probability that she has indigestion is 0.1, probability she doesn't have indigestion must be 0.9. Now, we are being asked to work out the probability that Judith had meat, given that we know she has had indigestion. So, knowing that she's had indigestion, what is the probability that she actually had meat? So this is the probability of meat and indigestion divided by the probability of indigestion. We're simply making use of the law of conditional probability. The probability of A given B is the probability of A and B divided by the probability of B occurring. So the probability of M and I, that's 0.2 multiplied by 0.8. Now, the probability of indigestion, this is interesting. We have to look at every possible path that results in indigestion. So that's this path, and this path here. So that is 0.2 multiplied by 0.8. Add 0.35 multiplied by 0.5. Add 0.45 multiplied by 0.1. And this works out to be 8/19 or 0.421 ... So let's have a look at the next question. A bag contains blue discs and red discs. There are 15 blue discs and an unknown number of red discs. There are more red discs than there are blue discs. A disc is taken at random from the bag and not replaced. A second disc is taken at random from the bag. You are given that the probability that two discs of the same colour are taken is the same as the probability that two discs of different colours are taken. Calculate the probability that two blue discs are taken, given that we know two discs of the same colour are taken. This is a really tricky question. There is a lot going on here. The end of this is a conditional probability calculation, and we've got quite a lot of unknowns here. Now, this could potentially be set up quite nicely in a tree diagram. So I'm going to say that there are n discs in total in the bag to start off with. So let's start drawing our tree diagram for disc 1, which could either be blue or red. Now the probability that it's blue is 15 over n, because at this point there are n discs in the bag, and the probability that it is red is n minus 15, because there must be n minus 15 red discs over n. If there are n discs in total, 15 of them are blue, n minus 15 must be red. Now, on to disc 2. Again, the discs could be blue or red. And let's follow the paths really carefully. So if we follow this path here, the first disc is blue, which means that there are 14 blue discs left out of a total of n minus 1. There must still be n minus 15 discs in the bag that are red, but now this is over n minus 1. If, however, we follow this path and the first disc is red, there are still 15 blue discs in the bag, but that's out of n minus 1. There must now be one fewer red disc, so that's n minus 16 in the bag over a total of n minus 1. Now, we're given that the probability that two discs of the same colour are taken is the same as the probability that two discs of different colours are taken. So let's work out the probability that the two discs are both the same colour. Now, that means we've got the probability of two blues, this path here, add the probability of two reds. So this is equal to 15 over n multiplied by 14 over n minus 1, and we want to then add on n minus 15 over n multiplied by n minus 16 over n minus 1. Now, the options for two different discs being taken must be covered by a blue-red or a red-blue path. Now, if the probability is the same in this situation, the two options, both the same colour and both being different colours, must have a probability of a half each. Otherwise, there is no way that this will add up to 1 otherwise. So it follows that 15 over n multiplied by 14 over n minus 1 plus n minus 15 over n multiplied by n minus 16 over n minus 1 must equal 1/2. And we have a common denominator, so we can simplify the numerator accordingly. So this gives me 210 plus n minus 15, n minus 16, all over n minus 1, which is equal to 1/2. And we then simply have a equation which we need to rearrange and solve. So I've simplified the numerator and I've cross-multiplied here, and I'm going to continue simplifying this. You can see this is heading towards a quadratic equation. So here we are, and we're going to carry on simplifying this. So we break this down to get n squared minus 61n plus 900 equals 0. Now, we're then going to input this straight into the quadratic solver on the calculator, in the graphical calculator, in polynomial mode, equation solving mode, and this immediately gives us n equals 36 or n equals 25, and we then have to select the appropriate answer. So remember, n is the total number of discs that were in the bag, and originally we know that the number of blue discs was equal to 15, and we know that the number of red discs is greater than the number of blue discs. So it's not possible for n to equal 25, as otherwise the number of blues would be 15, and that would be greater than the number of reds, which would have to equal 10. So this tells us that n has got to equal 36. So on to the last part of the question. Now that we know that n is equal to 36, calculate the probability that 2 blue discs are taken, given that 2 discs of the same colour are indeed taken. Now we know, without having to do any working, that the probability that both discs are the same has got to equal 1/2. It's how we resolved the last part of the question. So the probability that we get 2 blue discs is going to equal 15 over n multiplied by 14 over n minus 1. You can see I'm following these two lines on the tree diagram. So that's 15 over 36 multiplied by 14 over 35, which gives me a probability of 1/6. Now, this is a conditional probability calculation. We are working out the probability of getting 2 blue discs, given that we know both discs were the same colour. So this is the probability of event A given event B, which is the probability of A and B, so the probability that we have 2 blues and both the same, divided by the probability that both are the same. So the probability of getting 2 blues and them both being the same, well, these two conditions are both satisfied by the first condition occurring here. An and condition has got to be strict. We have to have 2 blues and both discs have to be the same. So the way that this is satisfied is if both discs are indeed blue. So that is 1/6. Now the probability that both discs are the same, we worked it out, it's 1/2, so it's 1/6 divided by 1/2, which gives us a very simple answer at the end of this question of 1/3. So on to the next example. A is the event Tom forgets to bring his calculator, B is the event Tom forgets to bring his maths book, and we are given the probabilities for PA and PB. Now, the probability that he forgets to bring both of those is 0.2. So this instantly sets us up very easily for a Venn diagram, A and B represented by the 2 circles. Now, the probability that he forgets to bring both is the intersection. So forgets to bring his calculator, forgets to bring his textbook, that's 0.2. So we can then fill in that the probability for this region is 0.3 because the overall probability for A is 0.5, and the probability for this region is 0.4 because the overall probability of B is 0.6. And that means that the probability outside here is 0.1. Now, part A, calculate the probability of event A given event B. Law of conditional probability tells us this is the probability of A and B divided by the probability of B. The probability of A and B is 0.2, the probability of B is 0.6, so that is an answer of 1/3. Now, for part B, we can simply apply the law of conditional probability again in exactly the same way. The probability of A occurring, given that B has not occurred, is the probability of A and not B divided by the probability of not B. Now, I'm going to use the Venn diagram to help me work this out. The probability of A and not B is this region here, so that is 0.3. Now the probability of B not occurring is 1 take away the probability of B occurring, which is 0.4, so I get an answer of 3/4 at the end of this. And then part C, state with a reason whether or not A and B are independent events. There are so many ways in which we can approach this. One way is to work out the probability of A multiplied by the probability of B, which is 0.5 multiplied by 0.6, which is 0.3. And then we look at the probability of A and B, which is 0.2, and the two probabilities are not equal to each other. So the probability of A multiplied by the probability is not equal to the probability of A and B, so A and B are not independent. We could also state that the probability of A and B is 1/3, which is not equal to the probability of A occurring, which would have to equal if A and B were independent. So on to what is the trickiest probability question in this suite of questions. So read the information really carefully before you start having a go at this and before you watch the video of the solution. So the 24 members of staff at the branch of this bank decide to start a lottery. They each pay £5 per week to enter the lottery. Each week, 3 of the numbers 1, 2, 3 and 4 will be placed in a random order by a computer. Each member of staff will make 3 different attempts entered into their computer workstation to guess the number that the computer has chosen. Show that the probability that a particular member of staff enters the correct numbers in the correct order in any week is 1 in 8. Now, I'm going to start off by thinking about the number of possible sets that could come up in the lottery. So 3 of the numbers 1, 2, 3 and 4 are being placed in a random order. So this means we're thinking about permutations, not combinations, because the code 1, 2, 3 is different to 3, 2, 1. The total number of possibilities is 4p3. How many permutations of 3 items can be produced from a total of 4? And that's equal to 24. So I want you to now imagine a tree diagram here. So the person could be correct on their first guess, which is a probability of 1 in 24. They've picked the correct code. There are then 23 out of 24 options where they could be wrong, but they get a second guess. Now on their second guess, they could be correct or they could be wrong. If they are correct on their second guess, then that's 1 out of 23 remaining options because we've assumed that the first option that they chose was wrong. So that means there are 22 out of 23 options left where they're wrong. And they get 1/3 go. And again, on their third go, they could be correct or they could be wrong. At this point, there's 1 out of 22 options, which would be correct, and there would be 21 out of 23 options, 22 options, which would be wrong. And it comes to an answer of 1/8, which is what we were expecting. Now, if exactly one person chooses the right numbers in the right order, that person will win a prize of all £120 paid by staff to enter the lottery. Remember, there are 24 people, they're paying £5 each to enter. If no one chooses the right numbers, or if more than one person chooses the right numbers, the prize will be rolled over to the next week. Now, let's take a look and see what's happening. Calculate the probability that someone will win the prize in the first week. So, essentially, this is a binomial distribution. So, if x is the number of people who get the correct numbers on any of their 3 goes, then x is binomially distributed with an n value of 24 and a p-value of 1/8. Now we want to work out the probability that x is equal to 1 person winning. 24 choose 1, or 24, multiplied by 1/8 to the power of 1, multiplied by 7/8, that's all the other people, to the power of 23. You can effectively think of it as one person's winning, which is 1/8, the other people are not winning, so that's 7/8 to the power of 23, and of course we need to multiply by a factor of 24 because any of the 24 people could win this prize. So that comes to a value of 0.13909 ... or 0.139 to 3 SF. Now, part C, calculate the probability that the customer services manager, Marak, will win the prize in each of the first 2 weeks. Now, this person's been named just to be really specific that the same person is winning the prize in each of the first 2 weeks. So it's actually just a variation on the theme of the previous problem. So the probability that Marak wins week 1, well, that means 1/8 multiplied by 7/8 to the power of 23. 1/8 is for Marak winning, and 7/8 to the power of 23 is for everyone else losing. We're not now multiplying by this factor of 24 because that was done previously to account for the fact that anyone could have won this prize, whereas we want specifically one person to win the prize. Now, this works out to be a small probability of 0.00579. Now, that's the probability that he wins 1 week. We want to now work out the probability that he wins both weeks 1 and 2. So if you think about it, that's going to be 0.00579 squared. So the week 1 probability multiplied by the week 2 probability. And of course, both of those are the same. So it's the same as squaring the value. So that's a very small probability, 0.0003358 ... So that would be 0.0000336 to 3 significant figures. Incorrect. So the last part of the question says, in fact, when the lottery started, nobody won until the prize reached £6,000. At this point, Milena, the chief cashier, won. Marak commented there was a 1 in a million chance of this happening to Milena. So nobody's winning, and remember the prize gets rolled over every single week. So let's work out what 6,000 divided by 120 is, because of course everyone's paying in £120 every week, so we need to know how many weeks this has gone on for. So 6,000 divided by 120 comes to 50. So this is 50 weeks. Now, in our previous working, we've worked out some very useful probabilities. The probability that one person wins was equal to 0.013900. So that's the probability that any one of the 24 people wins. Not a specific person, but any one of the 24 people. So the probability that no one wins is going to be 1 minus that probability, which comes to 0.8609 ... And I might well store this carefully in a calculator memory. These are numbers, so I've got them for later use as needed. So what we want to happen is that for 49 weeks, each of those weeks, no one wins. But in week 50, we want a specific person, Milena, to win. Now, we know that the probability that one specific named person wins is equal to 0.005795 ... It's the same as the probability of Marek winning 1 week. And remember, that's different to the probability of any one of the 24 people winning, because you're now not looking at multiplying this number by 24, because you're looking at one person winning. So that, of course, is the 1/8 probability for one person, that named person, 7/8 to the power of 23 for the other 23 people. So this probability overall is going to equal the probability that no one wins for the first 49 weeks, which is this number here, 0.8609 raised to the power of 49. Imagine a tree diagram with 49 branches on it, and each of those 49 branches is no one, no one, no one. You're doing 0.86 times 0.86 times 0.86. You're doing that 49 times. And you want to multiply that by the probability that one specific person wins, which is 0.005795. And that comes to an overall answer of 0.0000376653 ... So we want to compare that to 1 in a million, and actually 1 in a million is equal to 0.00006. So this is actually smaller than 1 in a million. So his comment